Okay, so what we've shown then is that direct application of the least squares estimator gives us an optimal mathematical solution. It's an estimator, it's a function applied to the data. But the question we now want to ask is it a good estimator? And to do that, we have to use inferential statistics that we covered in lecture 2 in order to investigate this. So we're now going to think not just about the mathematical solution, but about what that implies for the sampling distribution of the estimator. So we're going to look at the statistical solution. And there's really 3 important points I want you to take away in this section. The first is that least squares is a linear estimator. We'll define what that means in a moment. Secondly, the least squares estimator, we can write it in such a way that we can show that it depends on the error term, and therefore the properties of that error term are relevant to the estimator, and we're going to use those properties. And finally, thirdly, under a set of assumptions known as the Gauss-Markov assumptions, which concern the error term, the least squares estimator can be shown to be optimal, or what we call best linear unbiased estimator, blue, and it's also consistent. And again, we'll cover that in this section. Okay, so evaluating the least squares estimator. To do this, what we want to do is show that the least squares estimators, estimates alpha hat and beta hat, are optimal in the class of linear unbiased estimators. That's what we're going to do. So first of all, we're going to define what's meant by a linear unbiased estimator. Now, an estimator is linear and unbiased if it takes this form here. So unbiased, of course, because the expectation of the expression in brackets is equal to the true value of the parameter, and we covered that last week. But a linear estimator, it's said to be linear if the estimator can be written as a linear function of the y, values of y, where di are unknown fixed constants. And it turns out that our least squares estimator can be written in this linear form, where the di, the unknown fixed constants, take this form, xi minus x bar over the sum of the squares. And for that reason, when we seek to evaluate the least squares estimator, we can restrict our attention to the class of linear estimators, because that's the class that least squares falls in. That's the first point. Least squares is a linear estimator. Second point is the least squares estimator depends on the value of the error term. And this is very easy to show. So beta hat, we'll focus on beta hat, it's the ratio of the sum of cross products to the sum of squares of x, which can be written in this form here, linear estimation form. It's a linear function of the y's. We expand y and we get the error term here. So consequently, the statistical properties of this error term are crucial, because the properties of hat beta, that is its expectation and its variance, are going to depend on them. In fact, the sampling distribution of the estimates depends on the distribution of the error term. Now, these two properties of the estimator being linear and it depending on the error term are the basis of what's known as the Gauss-Markov theorem. And the Gauss-Markov theorem sets out 4 conditions under which the least squares estimator can be shown to be optimal. That is, it can be shown to be the best linear unbiased estimator, or what we call blue in the acronym. And the 4 conditions are as follows. First of all, the error term must have expectation mean. That is, its random noise distributed around a mean of 0. Secondly, and we've come across this condition before, the error term must be uncorrelated with the covariates. So its conditional expectation, or its covariance, must be equal to 0. Thirdly, the variance of the error term has to be constant for all I. So the variance of each individual element of the error term has to have constant variance. The variance is not indexed by I, because the variance does not differ over observations. And finally, the error term has to be statistically independent of one another. So the error term for observation I is independent of observation J for all I in J. So that's the Gauss-Markov conditions. What do they actually mean? Well, the way to interpret them is as follows. 0 mean error. The error term that we observe will sometimes be positive and will sometimes be negative. But what the first Gauss-Markov condition is saying is it shouldn't have a systematic tendency in either direction, because of course if it did, that would mean that there was something systematic in the error term, something that's a quantity, that's a non-zero quantity, and that we don't want that. We want an error term that's random noise. Now this condition of zero mean is effectively guaranteed as long as we've got an intercept in the model, and these expressions here show why that is the case. So that's one of the conditions that tends to be guaranteed. We don't really need to worry about it too much as long as we have an intercept in the model. But zero mean error, first condition. Second condition is what we call exogenous covariates. That is the variables in the model should be distributed independently of the error term or uncorrelated with the error term. Now, if they were correlated with the error term, that would imply that there's something systematic in the error term that affects our models, and we don't want the error term to have systematic components. We want the error term to be random noise. So that's really what that element of Gauss-Markov theorem means. Thirdly, the error term should have constant variance. No tendency for the variance to be more erratic in some observations than in others. Again, the idea here is that there shouldn't be something systematic that's causing the variance to be more erratic in some observation than others, because we want the error term to be random noise. And finally, there should be no correlation structure in the error between observations. So error term for observation I, independent of that for J. And towards the end of this part of the lecture, I'll explain some particular conditions under which these last three assumptions can be violated. Now, if the Gauss-Markov assumptions are met, then what we can show is that the least squares estimator is unbiased. That is, the expected value of hat alpha is equal to the true value of alpha, and the expected value of hat beta is equal to the true value of beta. And they're also the most efficient, or what we call best. The variance of hat alpha and the variance of hat beta are as small as possible within this class of linear unbiased estimators. In fact, they're uniformly minimum variance unbiased estimation as long as the Gauss-Markov conditions hold. And what I'm going to do now is have a proof to show you what Gauss-Markov is actually saying about the optimality of the least squares criteria. Okay, so what we're going to prove is that least squares is blue, best linear unbiased estimator under the Gauss-Markov theorem. Now, any linear unbiased estimator of the slope parameter beta has to satisfy this expression here. So it's a linear estimator, it's a linear function of the y, where these are the fixed constants, and the expectation of this quantity has to equal the true parameter value. Now we know that we can write the least squares estimator in linear form, where the unknown fixed constants are given by this expression here, xi minus x bar over the sum of the squares times yi. That in turn is equal to the covariance of x and y over the variances of x, as we've already seen. And we can expand y in this form here, so the covariance of x, and then we've just expanded y here over the variance of x. Now, by the rules of covariance, we can write this numerator in this form here. It's beta times the variance of x times the covariance of x and the error term, curly e. We can write this in this form here. And so, substituting this in up here, what we find is that beta is equal to, beta hat is equal to the covariance of x and y over the variance of x, which actually can be written as beta plus covariance of x and e plus the variance of x. Thus, if we take expectation, as long as Gauss-Markov condition 2 holds, then this expression here is going to disappear because the covariance of x in the error term is 0, and therefore the expected value of beta can be shown to be equal to the true value of beta under Gauss-Markov condition 2. This is a so-called identifying condition for unbiased estimation. Turning to alpha, the least squares estimate of alpha is alpha hat. It can be written in this form here as we know. We know that the expected value of beta hat is beta, so taking expectation of alpha hat and plugging this in here, we get alpha plus beta x bar minus beta x bar equals alpha. So the least squares estimate of alpha is also unbiased because it equals the true value of the parameter that we're trying to estimate. Okay, so that establishes that least squares is unbiased. Now we want to turn to this question of, is it best? Now, if the least squares estimator is a linear unbiased estimator, then that property there must hold, as we've already seen. We're going to use the rules of expectation and pull these unknown fixed constants out of the expected value. We're then going to expand y, and we get this expression here, which can be written in this form here. Now, this is saying that beta, the true value of beta, is equal to this expression here. Well, we can see immediately that can only be true if this quantity here disappears, and therefore the sum of our unknown fixed constants must equal 0. And it's also only going to be true if this expression here is equal to 1. So the sum of our unknown constants times xi must equal 1. And these are two conditions that we're going to use as constraints in a constrained optimization problem to prove that least squares has minimum variance. So let's turn to GM conditions 3 and 4. If they hold, we can express beta, the variance of beta, written in this form here, as variance of beta is equal to, well, we're just going to apply the rules of variance of a constant times a random variable, and that gives us the constant squared times the variance of the random variable. But under GM condition 3, the variance has to be constant, so we can write that as sigma squared, that's the variance of y, and therefore the variance of beta can be expressed in this form here, sigma squared times sum I equals 1 to n of di squared. So, to show that least squares is efficient then, all we have to do is find the di, d1 to dn, that have the minimum value of di squared, because this is what's scaling the variance of y, and that satisfy the conditions that we've set up here, that the sum of di xi equals 1 and the sum of di itself equals 0. So that's precisely what we're going to do. To do that, rather than minimize, we're actually going to maximize. And the reason we're going to do that is we can write this expression here, 1 over the sum I equals 1 of di squared, this is the quantity that we're trying to minimize, in this form here. So we're going to replace 1 by our constraint, and denominator remains the same. And all we've done here is plug our constraint into this quantity here. And the di, d1 to dn that minimize this thing also maximize this quantity above. So that's what we're going to set out to do. We're going to set out to maximize this. And the theory of maximization for a constrained quadratic function shows that the di that form the maxima of that problem, that constrained optimization problem, have to take this form here. And it's a nice form for us because it's got a non-zero constant times xi minus the mean of x. And we come across this expression a lot, of course, in the variance in the sum of squares. So using this result of the constrained optimization problem, the maximization of this quantity here, we can write sum dixi as, plug this in, sum over I, x, k times xi minus x bar, times xi is going to multiply by xi, equals, well, this quantity here, the sum of this quantity here is simply the sum of the squares. So the sum of dixi is equal to k times the sum of the squares. Now our first constraint says that this quantity must equal 1, and therefore k has to equal 1 over the sum of the squares of x. And thus, if we define d1 to dn by these quantities here, xi over x bar over sxx, this is just these directly derived from here, then we have a minimizer of di squared, which satisfies both constraints. This thing here will sum to 0. This, the sum of dixi will sum to 1. And that is in the form of the linear estimator. That is precisely the di that we defined up here. So what that shows is the least squares estimator we've shown in the first part here is a linear unbiased estimator. And through this process of showing that it has minimum variance, we've also been able to show that in the class of linear unbiased estimators, it has minimum variance. And that is why we describe the least squares estimator as a best linear unbiased estimator. Now, of course, that optimality of least squares is true only if the Gauss-Markov conditions hold. It's guaranteed to be optimal in the sense that it's blue as long as these conditions hold, and we've used them in the proof that we've just looked at. However, violations of the Gauss-Markov conditions frequently occur, and knowing how and when they occur can help us to avoid problems that would arise by incorrectly accepting least square specification. Essentially, when the Gauss-Markov conditions fail, we don't have to give up regression, we just need more complicated models. But I just want now to talk about some common violations of the Gauss-Markov conditions. First off, this assumption that the error term is distributed independently of the covariates, that's a common problem that fails in regression analysis. And it could happen, for instance, because we have a set of variables z that we don't observe. So they end up in an error term that comprises both gamma zi plus ei. This would be our error term if we don't plug those variables into the model. And as long as x is correlated with z, which often happens, then we're going to have an error term that's correlated with x, and Gauss-Markov condition 2 is going to fail. That's called omitted variable bias. Another problem that often arises is we've got a model in which we're interested in how x affects y, but actually the reverse is also true. Y has an effect on x, and as long as y has an effect on x, then x depends on the error term because we can expand y. And again, we have what's called endogeneity, so this exogeneity, the Gauss-Markov condition 2, which is the exogeneity condition, fails. Secondly, heteroscedasticity, where we're saying the variance of the error terms is non-constant, and that often arises in situations where the values of variables vary quite substantially in different observations, and that causes homoscedasticity not to be realized in practice. This is a condition which can be dealt with fairly easily, actually, unlike this condition, which is a bit more tricky, but commonly occurs. And it can be identified by looking at plots of residuals, is the way to take a look at whether heteroscedasticity is a problem. Finally, correlated errors. So we want the error terms to be independent of one another. Again, this condition is often violated quite often in time series models where the error term for observation t is correlated with observation t minus 1 and observation t plus 1. So there's a correlation that's happening in the errors over time due to things that are emitted from the model. It also happens in models that have, for instance, based on spatial data, where observations for places that are closer to one another tend to be more highly correlated than those that are further away. So lots of reasons why this condition also fails. Now, under the violation of this condition, endogeneity, the first condition, the least squares estimates are actually biased. So this affects the unbiased property. Heteroscedasticity and correlated errors don't affect bias. The estimates will still be unbiased, but they'll be inefficient. So they won't no longer have the property of being minimum variance estimates. They won't be the most efficient ones we can achieve. We can do better by trying to do something about the heteroscedasticity and correlation errors by introducing that into the model. And we'll talk about that maybe in some slightly more advanced lectures. Final point I want to make is that we've shown under the Gauss-Markov conditions that least squares estimator is best linear unbiased. It's also consistent. And this can be shown by simply applying a law of large numbers to the least squares solution. So remember, consistency is a large sample property, and all we're going to do is use asymptotics, the law of large numbers, to say, beta equals, we can write it as n minus 1 times the sum of the cross products, n minus 1 times the sum of the squares. In probability, these two quantities, through a law of large numbers, because these are simply expressed as averages, converge in probability to the covariance of x and y over the variance in x, which equals beta. And as long as this expression here equals 0, then under Gauss-Markov condition 2, then the value of beta will converge in probability to the true value of beta as n approaches infinity. For the intercept, the least square solution is given by this expression here. Applying a law of large numbers, we can say that the mean of y, this expression here, converges in probability to the expectation of y, which is equal to alpha plus beta expectation x. If beta converges in probability to beta, as we've said here, then we can plug beta x in probability for this expression here, plug that in there, and what we're going to get is that alpha hat converges in probability to the true value of alpha as n approaches infinity.